Hello everyone, my name is Aritrash and welcome to a new video. So this video is actually a part of a series called Computer Architecture. It's on my channel. This is technically the third video from the series. The previous two videos have the topics of computer architecture, the basics, history of computing, and then we have got some semiconductor physics. If you want to take a look at those things, please check out my channel. Check out the playlist. I will provide a link for that in the description. I won't go into much depth into what we learned in the previous videos. If you would like to check that out, please do it. And let's take a look at this video, which will be on logic and binary systems. So this video will include, as you can see, binary representation, logic through binary, and gates from MOSFETs. And we're taking a look at the second abstraction layer of computing. So here we go. So binary and logic. So binary number systems include the numbers of 0 and 1. In digital logic, the 0 is called a low, while the 1 is called a high. A low signal is generally associated with a ground or relative ground signal, or a general lower potential, usually depicted as VSS or ground. A high signal is generally associated with a higher potential, generally depicted as VCC or VDD. Sometimes a signal can be in between a high and a low, known as a floating signal, and they require pull ups or pull downs. So let us take a look at the logic operations that we can perform. Just a side note, I will be a little faster in my speech today because this chapter is pretty long and I just don't want the video to be really long. So, yeah, if you're having some issues, please let me know. If I have to make the videos, I can make the videos a bit longer and talk slower, or is this pace okay? So let's look at the logic operations. We can perform certain operations with binary numbers which are not arithmetic. They include operations like bit inversion, which is not, the and the or. These three operations are called basic operations. Then we have the NAND and NOR, known as universal operations, since any basic operation can be implemented using these operations. We also have exclusive operations such as XOR, XNOR, and even ZAND, which are exclusive operations. So let us take a look at the De Morgan's laws. For any operations and conversion efficiency, we have a pair of laws called the De Morgan's laws. So the first law says that if you invert an AND operation, the resulting result would be an inverted A and an inverted B ORed together. That's a plus. And the second law says that if you invert an OR operation between A and B, then the output will be just the ANDed not A and not B. The core idea is break the bar, change the sign, flip and or when applying the negation to a group, or push the negation in to simplify expressions, making complex logic easier to handle. When you do some sums regarding De Morgan's laws, you can easily understand the viability of this law and why this is so useful. Let us take a look at logic gates. So, logic operations can be made using devices built using transistors and passive components such as resistors and diodes. Such devices are called logic gates. Different logic operations require a different number of transistors and other components along with design. Every gate also needs to have a section called an output buffer, which consists of two transistors and a diode. The job of this section is to pull up the high signal to VCC and to pull down the low signal to ground. So let us take a look at the logic families. With the evolution of computers in the last century, the types of transistor logic families used for the manufacturing of gates have evolved. Some older techniques included RTL, that's resistor transistor logic, DTL, which is diode transistor logic, TTL, which is transistor transistor logic, which dominated the industry until the 1980s. We also have the ECL or the ETL, which is the emitter couple logic kind of a thing, which is pretty fast in the standards of the 1980s industry. The modern or the post 1980s technique of logic families is known as complementary MOSFETs or CMOS. This uses a pair of P type PMOS and N type NMOS MOSFETs to function. Transistors as gates. A single bipolar junction transistor BJT with a resistor can be used to build a simple NOT gate. The input signal is sent to the gate of this transistor. The emitter is connected to ground, whereas the VCC is connected through a resistor to an output node and also to the collector of the transistor. When a high signal is applied to the base, the transistor turns on and current flows from the VCC directly through the transistor to ground, so no current flows through the output. Hence, when 1 is sent to input, output returns a 0. Now, similarly, a refinement of the RTL design, usually found in the 74 series logic gates, is the TTL design. Here, 4 transistors are used. The first transistor, Q1, is always on as its gate is connected to VCC using a current limiting resistor. But the transistor being inverted, input to an emitter, output to collector, creates a high impedance buffer so random signals can't pass through. The Q2 transistor in the same RTL design with R2 connected to VCC and an output node. The emitter of the Q2 is connected through a pull down resistor to ground and a node. The two nodes VC and VB, as you can see in the image, are connected to two transistors of the output buffer section. The top transistor of the output buffer, Q3, has its collector connected to VCC through a current limiting resistor, and its emitter is connected to the output node through a diode and to the collector of Q4 and the base to VC. The bottom transistor of the output buffer, Q4, has its collector connected to the output node of its emitter and its emitter to ground, base to VB. You can take a look at the image given in the side to have a little imagery in your head that how this actually kind of works and not just kind of listening to me rambling along. The output buffer makes sure that the high signal is close to VCC while the low is close to ground. The TTL or RTL designs are prone to I squared R heat losses, which are also known as copper losses, due to the inclusion of resistors in the design. Modern computers use complementary MOS, CMOS, which is the connected system of PMOS and NMOS field effect transistors. For a CMOS NOT gate, the input signal is fed into the gates of both the FETs. The PMOS source is connected to VDD and the drain is connected to the output node and the NMOS source, whose drain is connected to the ground. The CMOS gates are much resilient to noisy signals which often doesn't require buffers. Majority of the gates in the modern computers are NANDs and NORs since they can be used to perform any logic operation. A CMOS 2-input NAND gate has two pairs of CMOS, each having one PMOS and one NMOS. The number of inputs determine the number of CMOS pairs. Every input is sent to the gates of one pair of CMOS, both the PMOS and the NMOS. Every NMOS source is connected to VDD and the connected in parallel. All the NMOS are connected in series, finally to ground for the last NMOS. The output is connected to the connecting node of the CMOS. Now let's take a look at active high versus active low. Across the logic spectrum, certain gates are labeled active high, whereas others are called active low. Functions or systems that require a high signal to function the way it's intended to is called an active high. Similarly, systems that require a low signal to function the way it's intended to is called an active low. An active low input is depicted with a small circle on the end of the pin, or the pin name has a circle has a bar on top. As you can see in the image, you can see that the reset pin has a bar, or the pin 4 has a little circle on that, whereas the circle on the output pin depicts an inverted output. So it has to be the input rather than the output regarding the circle. Otherwise, you can get a little bit confused. Let us take a look at NAND as NOT. NAND gates can be used as NOT gates. The way it's usually done is by shorting or connecting both the inputs of a 2-input NAND gate. When a high signal is sent to the input, the NAND receives a high on both the inputs, forcing the output to be low. Generally, this is not how most computers implement the NOT gate, since a single NOT uses 2 transistors but a NAND uses 4. Manufacturing a NOT is cheaper in terms of both materials and effort. Now, NAND as AND. NAND gates can be used to implement the AND function. The NAND gate is simply an AND gate with an inverted output. So, a NAND gate with its output connected to both the inputs of another NAND gate makes an AND gate. In CMOS technologies, the AND gate is generally built using the 4 transistor NAND setup connected to the 2 transistor, not to the output. Because generally, otherwise, you would be having a much bigger, 4. If I use 2 NAND gates, then I have to use 4 plus 4, 8 transistors, whereas, the NOT actually makes it, cuts down 2 transistors. So now it's 6. So that's, more um, cost efficient and also energy efficient. Now let's take a look at NAND as NOR. Sorry, NAND as OR. NAND gates can be used to implement the OR function. Two inverting NAND gate setups are used to invert the incoming signal, and a final NAND is used to combine those two signals to form the final NANDed signal. The inverted A and B, A bar and B bar are NANDed to form the A bar B bar whole bar, which using De Morgan's laws can be rearranged to A plus B. In CMOS, we can use two inverting CMOS setups coupled with a NAND setup to form the OR gate with 8 transistors. Now, NAND as XOR. NAND gates can be used to implement the exclusive OR function. Each input signal is fed into a common NAND and one exclusive NAND. The common NAND just outputs its signal AB bar to both the exclusive NANDs. Now, don't just, what should I say? Don't um, confuse exclusive NAND with X NAND or something, because I am just using the exclusive NAND as a reference term, right? It's not a real gate, it's just a NAND gate, right? So the exclusive NAND gates output these signals A bar, A into AB bar, now that whole bar, and B into AB bar and whole bar into the final NAND, you get the vision. The final NAND's output is A XOR B. The XOR gate is a fundamental gate for ALU design. We will see that in the upcoming episodes if I do make one. So, oh, that's the end. Damn. Things to remember. De Morgan's laws are essential for complex logic conversion. NAND gates and NOR gates too can be converted into any logic gate. Both have their own pros and cons, but in recent days, both are used to build various systems such as memory modules. One must not forget the importance of MOSFET in computer engineering, as I actually talked a lot about MOSFETs in the previous video. If you would really like to check that out, please do. In CMOS technologies, the core idea remains the fabrication of lesser components per operation. If a job can be completed using 2 transistors, 4 transistors may not be fabricated just for that operation. And use of gates are completely determined by two factors: cost optimization and operational efficiency. So uh, so the next video would be on semiconductor fabrication. So all the lithography nerds, you can come. Yeah. So thank you for watching, everyone. If you really like the content that I make, I greatly appreciate it if you would like and subscribe, the usual YouTube terms. And peace.